Good morning or good evening, depending on where you are. So welcome to the webinar, How Digital Simulation is Used to Build and Validate Autonomous Vehicles. First, let me introduce myself. My name is Jean-Charles Legal. I'm the business developer worldwide at OPAL-RT ITS, Intelligent Transport Systems. I will be responsible for hosting this webinar today. I'm glad to announce our special guest who will be presenting today, Untitled, digital validation developer at Group Renault, and Hervé Pollard here with us is my managing director at OPAL-RT ITS. He will answer your question at the end of the webinar. So we will have three parts in this webinar. First part, I will present you why we talk about simulation and our RT Lab orchestra. On the second part, will be a use case with Renault. Johan Dutel will explain you that. And on the last part, at the end of the webinar, we will have a question and answer period. So please feel free to start sending your question. For this, just you can use the question tab that is located in your dashboard. If you want more information about this presentation, you can access on our website and just select the webinar. So now we can start the first part of this presentation titled Technological Challenges for Autonomous Driving Systems Validation in Heterogeneous Environments. As everybody knows, the driving system ADAS and AD add complexity in the traditional system of automobile. In order to this complexity, there is an incidence on development product, the conception process to validation and certification. In addition, we have, on the one hand, growing complexity that leads to increasing time and cost of the product, and on the other hand, the placing on the market forces for each car manufacturer, it's a real challenge. This challenge is truly important because they touch on societal aspects to have accepted the ADAS and AD system by the general public, which will be obviously marked by public safety tests. So this presentation will be organized as follows. The first part will focus on the context and issues related to testing and validation of complex systems, such as those embedded in intelligent and connected vehicles. The second part will focus on the importance and impact of simulation validation. We will also talk about the need to process simulation and real-world equipment at the same time and same level to ensure the representativeness of unit tests. On the third part, will be focused to the added value of OPAL-RT in this validation process, whether it's the support of multiple hardware platforms, our RT Lab and Orchestra tools, as well as the link between the simulated and the real. And to conclude this presentation, we will conclude by citing the steps we believe should be taken to improve the existing solution or future axes to be taken into account for ADAS AD validation. So, vehicles complexity. Vehicles are more and more complex, hosting a multitude of sensors, actuators that interact through communication interfaces, and can include multiple hardware architectures on which heterogeneous software works. The vehicles, in addition to integrate systems related to comfort, safety, and entertainment, are combined with ADAS and AD architectures, making complex reliability that leads to some safety system, redundancy, and added complexity. It's interesting to note that these systems are high added value and are generally driven by trends, and each car manufacturer wants to be the best one, which will offer the best advanced solution to make difference on the market. Reducing costs versus accelerating validation. On the one hand, a product with a high added value, and on the other hand, cost gated by the automotive market focused on volume. The studies estimate that the cost of issues will be represent till 50% by 2030 of the total cost of the vehicle, leading us to optimize and take advantage of the most efficient way to test vehicles. The validation process must be optimized and inspired by new testing methods. Heterogeneous architectures. So another aspect that we should take account is the heterogeneity of the architectures that is integrated into vehicles today. There are a multitude of communication technologies, buses, and interfaces, many subsystems designed to operate at different speeds, but to achieve a common goal. It's also interesting to note that a sensor can provide a system essential to life and at the same time serves entertainment. Hence the need to differentiate and prioritize security-related and non-priority streams, adding complexity. Communication and data fusion. It should be noted that communication devices are considered like a sensors and a rich source of information. They may collect information from other vehicles and roadside units for navigational purposes and take into account information essential to safety. Wireless communication technologies enhance vehicles' interaction with their environment. Opening a door to a closed system can pose a security threat if it is not adequately protected and or is not isolated from other onboard communication networks. With artificial intelligence, data fusion is the senses and brain of the intelligent and autonomous vehicle. Data fusion is a tool that takes advantage of several homogeneous and heterogeneous sensors isolated to better understand the vehicle's environment. It can be based on a simple calibration processes, and either it can be complex systems that involve in-depth learning. This aspect can be a great added value if they are designed, but can be a big challenge for the testing phases because nowadays is no clear way on how to test AI systems. But with the introduction of such complex onboard systems related to active safety, perhaps the test procedures could move to more adequate and conservative testing method that requires no vehicle crash, etc., inherited from software and aerospace engineering. It's also interesting to mention that AD is supposed to be more effective than human driving, and the idea behind is to reduce accidents and costs. Apart the answer to the problems mentioned above can be summarized in one word: simulations. So you can say why. The simulations are easy to adapt, have a lower cost than the deployment of actual prototype and validation. It's also a way to detect design problems and defects in the early stages of product development, making it easier to modify designs and adapt accordingly. It offers an easy way for systems interoperability. Some materials can be designed and evolving into take account changing of design or recent environment. So now you can think, how? One thing is sure, there isn't exist a full solution complete based on a simulation, as each simulation environment has its own advantages and disadvantages. Some of them are really powerful to simulate sensors and the environment, while others are made to accurately simulate vehicle dynamics and onboard systems. Which brings us to a primary consideration of how to leverage the power of everyone and have them serve the same purpose to be a powerful tool that addresses ADAS testing demands and concerns. Another aspect is the ability to ensure repeatability and optimization of tests in order to make the most of these tools and use them effectively at a cost lower than a real test. In addition, these tools must take into account the different applications that coexist in the same environment and are subject to different time constraints. It's also a good idea to take advantage of the same tools throughout the different phases of product design up to the final stages of testing to reduce the risk of error between system behavior in the simulated environment and the real environment, and to take into account every small detail that can affect the performance of the systems. The coexisting of all systems can have an impact on the load of processors and different buses. The simulation, to what extent? The massive simulation is the answer to the billion of kilometers that are required for any ADAS test. Resources are virtualized, and the main goal is to get a large number of simulations. The post-processing phase allows the sum measurement to be extracted in order to analyze each scenario and possibly correct undesirable behaviors and recreate scenarios. This phase can be done by AI. A common approach to this is to test the overall architecture by segmenting it into subsystems that can be independent of each other and ultimately combine all critical scenarios on a smaller number of scenarios that can be replayed to assess the system's overall performance. So, it brings us closer to the barrier between the real world and the simulated world. And here, we can introduce the concept of co-simulation based on a combination of simulated equipment sensors and their interaction with a real issue. Now, we'll see how OPAL-RT fits into the response to the problem cited and its solution for simulation. RT Lab is a suite of tools that allows you to model, compile, and execute your models under different types of targets. It's a real-time architecture for the validation of distributed systems and subsystems. It follows you from the design phases to the deployment phases and manages the execution of your design. With RT Lab, the performance validation task can start with a traditional Windows target. That is just an ordinary computer, which use the power of RT Lab and scale up a massive simulation deployment on a cloud-based architecture with thousands of virtualized resources. Orchestra is a higher level application that sits above RT Lab framework and is essentially a communication layer that improves RT Lab's performance in terms of data exchange between the models and system tested. It's a plug-and-play tool for mapping data and synchronizing between environment and co-simulated systems. For its current version, Orchestra supports customer based on models like Simulink, AMASIM, or customer based on C code. Orchestra is a software focused on the data to facilitate interoperability and integration. One of its strengths is the ability to manage data exchange and synchronization without interfering with model execution and without introducing additional processing delays, thanks to the using of shared memory with limited access latency. RT-Lab Orchestra is a high-performance co-simulation framework optimized for real-time HIL simulation and a high-performance laboratory-wide supercomputers using private and public server. So today, this presentation focused on the MIL, model in the loop, and SIL, software in the loop. But as you know, it's not enough to validate autonomous driving system. The next step will be the validation of the real components like sensors or hardware issue. In the HIL mode, the complex models have to run in real time, and this challenge is the DNA of OPAL-RT. So in the next webinar, we're pleased to announce what is our new solution to continue this AD validation based on an NI platform and OPAL-RT expertise. So we are at the end of this presentation. Thanks a lot for your attention. Don't hesitate to send your question on the tab in your dashboard. And now here's our special guest, Johan Dutel.